Hello everybody and welcome back to Calculosity. I'm your host Corey, and today we're going to talk about calculating limits graphically. So previously we talked about limit notation, which for a refresher, that's going to be y is equal to limit of some function as x approaches some value. Right? That is our basic limit notation and what it looks like. So now what we have to do is we have to take it a step further and see what does this mean and how does it apply graphically. So this is going to be a rather important step on the AP exam, so we'll want to cover this in some detail. So let's pretend we have a graph here, alright? And we have some function that, does some swoopy thing, like so. So we've got some a value here. So this a value is going to be correspondent to this y value right over here, correct? So now, if they came up to us and said, hey, we would like the limit of this function, which is going to be y equals f of x, we would like the limit of y equals f of x as x approaches a. So this is how it would be notated. They want us to figure out what is the limit of f of x as x approaches a. And to start, let's do it from the left-hand side. So a minus. So graphically what this means is we should consider that we're going to be walking across this line towards a on the right-hand side. So I'm going to put little tick marks here, and we're just going to wander towards the a value. And hey, when we're finally there, we'll never pass it. But when we finally get to that a value, we want to figure out what y value are we at. And well, in this case, the a value corresponds with a y value of f of a, which is the function value at a. So, that being said then, because as we wandered closer and closer to the a value on the line, pretending we're running our finger against the line towards the a value, we got to y equals f of a. So thus, our answer is going to be f of a. And you'll find that this is pretty much always going to be the case in a function that's well behaved, that doesn't have any asymptotes or holes or anything like that. So, now we could say something like, well, perhaps a is equal to x equals 4, and this f of a is equal to y equals, 6. So then if we were to put this into appropriate notation, this would be the limit as f of x, limit of f of x as x approaches 4 from the left. And that would be 6, because we're running into the y value 6. Now, if we were to do it from the right-hand side, we'll see that yet again, because this is a nice, well-behaved function and it doesn't have any holes or asymptotes or anything like that, which we will get into the definition of a little bit later if you're not familiar, we just have to walk across the line from the other side now with these little tick marks, and we're going to get closer and closer in. The important part of a limit is that we never actually reach that point. So if we're going to 4, we're never actually going to reach 4. We're going to get very, 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 very close to 4, within 0.000000000, etc., 1 of that value. So we're getting very, very close, and as we get closer and closer, we see that our y value is yet again leveling off at 6. So we'll find that here in this case, our limit on the other side coming from the right-hand side, the values that are larger than x equals 4 in this case. So the limit of f of x as x approaches 4 from the right-hand side, yet again going from like 4.1 to 4.001 to 4.0001, that's going to level us off also at y equals 6. So perfect. So what this means for us then is because the left-hand limit and the right-hand limit are equivalent and they're both heading into 6, we can be 100% confident that the limit overall as x approaches 4, with no plus, no minus, the general limit as x approaches 4 of f of x is going to be equal to 6. What that means is that if you take your finger on either side of that a equals 4 and you run it along the graph, they're going to meet in the same exact place, which is y equals 6. Now let's consider a function that doesn't have that kind of nice behavior. So let's consider a new function. Oop, that is a little too thick. Alright, let's consider a new function as so. So this function does something like this. This function has a hole in it, what's called a jump discontinuity, which we can go into a little bit further, but a jump discontinuity is a very, very special situation in which the line is not constant. We can't run our finger from the left side to the right side of this hole because there's this massive jump. We'd have to pick it up. So because of this now, if we say this is x equals 4, we're going to find that there's some weird behavior when we do our limit notation. So if they say find us our limit from the right-hand side of, we'll call this g of x. If they say find our limit from the right-hand side of g of x as x approaches 4, and the right-hand side yet again is going to be the plus sign, we're going to run along the right side of this function, like so. We're going to get very, very close to this dot. And when we finally get there, we're going to see that our x value, or our y value rather, which we don't have exact values, but we can call this, say, 8. So say this is y equals 8, right? That's what we approached on the right-hand side. So this is 8. But we're going to notice already that if we're coming up on the left-hand side, so if they say to find the limit of g of x as, forgive me, I've got handwriting of a doctor. So if they tell us to come up on the left-hand side of g of x at x equals 4, we're going to notice that our answer is going to be a little bit different, because now as we come up on this left-hand side towards this hole, reminder, we're always getting very, very close to 4, but we're never going to touch it. So we're never going to touch that hole. What the hole represents is that there are values all the way up to that x equals 4, but not at it, much like how the limit works. So we're going to get closer and closer to that hole, but we're never going to touch it. And so we're going to see that our x value, or our y value rather in this case, is getting very, very close to whatever the y value is here, which, for the sake of understanding, it looks like about halfway, we'll say is 4. So what that means for us is that our left-handed limit is 4, but our right-hand limit, well, that's 8. And since they don't disagree, and like I said, we have what is called a jump discontinuity, the general limit, which is the limit without any sidedness, which is just notated as x approaches 4, this does not exist. This is a case in which when you run your finger on both sides of the graph and you bring them together, they don't meet at the same exact point, and when that occurs, the limit does not exist. And that's an issue. So, that's all fine and dandy, but not every function behaves quite so nicely as these ones. So, perhaps what we should do is we should dig into a different kind of function, a function that approaches infinity somewhere. So this will get us into what are known as asymptotes. So let's get into it. We're going to draw another function here, and now we're going to have a function that looks a little bit different. So what we're going to have is what they call an asymptote, specifically a vertical asymptote. So let's get a look at it. So what a vertical asymptote is essentially a line that runs through an x value. So here, we're going to say that the vertical asymptote occurs at x equals 3, for example. And so, we're going to pretend now, or rather draw, that as our function snakes along, it's going to get very, very, very close to that asymptote, but it's not going to touch it. That is important. So as it goes off into infinity, into the vertical direction, it's going to get very, very close horizontally to x equals 3, but it's not going to touch it. And then on the other side, it's going to do the same exact thing, but in reverse. It's going to come back down, like so. Understand, my handwriting is not great, but this is the general idea. So it's peaking up, and it's never touching that value x equals 3. So now, if we want to calculate our limit, it's going to get a little bit interesting. So, let's start by trying to figure out what our left-hand limit is. So our left-hand limit here is going to be the limit, and we're going to call this function, I don't know, we can call it h of x, since it's the third one we've dealt with. So we're going to take the limit of h of x as now x approaches 3. From the right-hand side, we'll stay consistent here. So on the right-hand side now, we're going to get our tick marks back out, and we're going to work towards this x equals 3 here. We're getting closer and closer and closer, and you're going to find that the closer we get to 3, the closer we get to some sort of infinity. We're getting really massively large as we get towards that value 3, and it's going to keep getting higher and higher, and it's never going to touch x equals 3. That line, that asymptote. So, as a result, we're working toward infinity. Yes, infinity. Now in limits, infinity is going to be very important. Now it's not an actual number, it's more of a concept that we're getting very, very, very immensely large. Now when it comes to practical applications where we're looking at graphs and things, we can consider infinity to be a very massive large number, like 100,000 or a million or 1/6 trillion, whatever makes you happy. That being said, it's an extremely large number, and that's where we're headed to. Now, on the other side, we're going to work at it again. So now we're going to do the limit of h of x as x approaches 3 from the left. So what that's going to be is we're going to take our tick marks back out, and we're going to work towards x approaches 3 on the left-hand side of this graph. And so mind you, our x values are moving inwards toward 3. And we're yet again getting up and up and up and closer and closer and closer to this infinite value. We're getting massive. It shouldn't take a whole lot of steps before we get up to million. So that being said, we can conjecture that we are moving towards, yet again, infinity. And as we saw previously, because the left-hand limit and the right-hand limit are equivalent and they're both moving towards infinity, this is a little bit tricky because your fingers will never come together when you're running them up the graph to see if they meet together. But this is an important little exception, kind of sorta, to remember when you're doing limits, is that these come together nonetheless. And if your left-hand limit equals your right-hand limit, whether it's infinity or negative infinity, or 0, or whatever it may be, the general limit is then going to be the same value. So remember that. If your limit on the left-hand side, notation-wise we'll go through this, as our limit on the left-hand side equals our limit on the right-hand side. So this is a little bit of notation for you guys. Since the left-hand and the right-hand side are equal, this just means therefore let's jump back a second here. We'll say that our limit on our left-hand side and our right-hand side are equal to some value a, and therefore our general limit is going to be equal to the same exact value a. So as x approaches 3 without any right or left, it's still going to be the same exact value a. And that's going to be the case any case in which your left-hand limit is equivalent to your right-hand limit. The general limit exists, whether it's a finite number or an infinite number. Alright. Now the same kind of behavior applies when we're moving into the infinite direction in the horizontal axis. So here we went to 3. But let's consider now that they asked us to do the limit of h of x as x approached infinity. Well, previously we were working with a finite number, but here we're working with infinity. Well, what that means for us is that we want to consider what's happening as x moves way over to the right, as far as we possibly can go. And what happens then is we can conjecture that this line is going to keep on getting closer, and note if this were a teacher's exam or something like that, they would have a really nicely drawn graph that is really, really accurate, and you can really tell that it's getting closer and closer to 0. But here we can conjecture that the graph is going to get super close to y equals 0. And because it's getting closer and closer to y equals 0, as we get further and further away from x equals 0, as we get towards x equals infinity, we can then conjecture that we have what is known as a horizontal asymptote. A horizontal asymptote. We'll write that out there. Alright, so this is a horizontal asymptote, and it says that up there. So a horizontal asymptote is an asymptote that is horizontal. Previously we dealt with the vertical asymptote. Yet again, I have kind of crappy handwriting, but we have a vertical asymptote over there, and a horizontal asymptote here. So, in this case, our limit as we go off to infinity, reminder, it's always going to be a y value that it's going to spit out when we're plugging into this function. So, the limit is going to be 0, because we are heading off into the y equals 0 direction. Mind you, the horizontal asymptote can be absolutely anywhere. If this line smoothed off at y equals 6, then that would be the case. So something like this, for example, if the function did this instead, well then that would be smoothing off at, say, perhaps y equals 6, something like that. So it doesn't have to be 0. The same exact thing can be done in the negative direction as well. So if we perhaps have the function do something like that off in the negative direction and asymptote off at 0 again, we can notate that as saying that the limit of h of x as x approaches now negative infinity, it's still going to be 0. Now be careful, you can't really have sidedness to these limits, so it is incorrect to say as x approaches infinity from the left-hand side or right-hand side. It's sort of agreed upon that an infinite value is really, really large, and you can't exactly approach it from any given side, think that you wouldn't be able to take your fingers and map out the opposite sides of some infinite value because it's not really a number, it's more of a concept. So you can't point out an infinity and then run your fingers up to it. So we just have to think x approaches infinity and x approaches negative infinity, never from the right side, never from the left side. And really that's all we need to know about dealing with limits here, whether it be an asymptote or a jump. We know now the behavior of either situation. Alrighty, so there's one final exception, however. When we're going on a horizontal and we're looking for the limit as x approaches infinity or negative infinity, we need to consider periodic functions, things that we learned in trigonometry like sine, cosine, perhaps something like tangent as well, functions that are going to continue going off in some direction, and they're not going to reach any specific point. So let's look at that. And they don't even have to be periodic functions necessarily either. So let's think the horizontal limit in a function like this. Now this function, it appears to be centering off at a specific value. So this one right here, since the hills are getting smaller and smaller and smaller, and they're oscillating around some given value, say this value right here in the middle, we would say that the horizontal limit would equal to this value, say a, as we go towards infinity. But not every function is going to look that nice, right? Some functions are going to be like, say, a parabola. A parabola does something like this. And now if we figured out what the limit of this parabola was, we can call this q of x. So if we have this parabola right here and they ask us, what is the limit of q of x as x approaches infinity? Well, it's not going to any specific value as it moves off into the infinite direction. So we're going to want to think we're heading this way. Oof, what an ugly color. We're headed this way, right? We're going to the right-hand side. And so as we do that, our value here is getting higher and higher and higher, and it doesn't really appear to be approaching any specific value because it's not. It's just going to get infinitely and infinitely larger as we begin plugging in a larger and larger value. You can consider if you were to plug into x squared, which is the function of a parabola, something like x squared, or in this case maybe x squared plus 10 because it's not centered at the y-axis. So if you plugged in 1,000 here, it would just be 1,000 squared plus 10. It would get larger and larger and larger, and it wouldn't really level off like a horizontal asymptote would. So in this case, our limit as x approaches infinity is going to be infinity. So we have a lot of infinities to deal with here. But remember, this infinity, the infinity on the right-hand side, this is a y value. This infinity down here is an x value. This is an important distinction to always remember, that what we're plugging in as x approaches is an x value, and what comes out is a y value. So that means that as our x value approaches infinity, our y values are getting much, much, much larger. And if we forget to draw this distinction between x's and y's, we could find ourselves very, very lost. And so the same behavior can be noticed in functions that are actually bounded. Functions like I mentioned previously, sine and cosine. So let's look at a cosine curve. A really, really sloppy cosine curve. So something like this. So what a cosine curve is going to do is, if you remember trigonometry at all, is it oscillates between positive 1 and negative 1. So this curve is going to oscillate between positive 1 and negative 1. And it's going to do that forever and ever and ever. It will never stop. So as our x value moves off towards infinity, like so, in this direction, we're going to find that the y value never ever levels off, much like the parabola which goes off to infinity, but this y value does not go to infinity, nor negative infinity. This is going to keep on happening. We're going to be able to find a point towards infinity that has a value of 1. We're going to be able to find a point towards infinity that has a value of 0. It's just going to keep on doing the same oscillatory behavior as it gets further and further. And as a result, we're going to find that our limit of this function, which we can call r of x since I'm running out of letters in the alphabet. So as we approach r of x, or rather as x approaches infinity for function r of x, we're going to find that the function actually does not have a limit. It does not exist. Why is that? Well, like I said, there is no single value that we're moving towards as we get further and further away on the x-axis. As a result, we're not moving towards infinity, we're not moving towards negative infinity, we're not moving towards a finite number. So the only other option is that we're not moving towards any number, which does not exist. Remember that these values here that are spitting out of the limit calculation, they can only be a finite number plus or minus infinity, or does not exist. And if it doesn't fall into either a finite number or plus or minus infinity, oh, forgive me for cutting that off. If it doesn't fall into a finite number or plus or minus infinity, it has to be, does not exist. And with that being said, I think we've covered about everything. We've dealt with limits as x approaches infinity, we've dealt with limits as y approaches infinity, we've dealt with limits as x approaches either side of a finite number, as y approaches either side of a finite number. So that's really everything. And there we have it.